Hello, my name is Wei Dai, and my talk today is on the multi-base discrete logarithm problem, type reductions, and non-running proofs for Schnorr identification and signatures. Then this is joint work with my advisor Mihir Bellare. The Schnorr signature scheme is one of the earliest known number theoretic signature scheme, and it was first proposed by Schnorr back in 1991. However, somewhat unfortunately, due to past patent status, it did not see practical adoptions until recent work of EDDSA, which is based on Schnorr, by Bernstein et al. Back in 2011. Now it is in the standardization process and is also widely deployed among numerous applications, protocols, and platforms. Compared to DSA, the Schnorr signature scheme enjoys a rich body of research, not only supporting its security but also extending into other applications. It was first proved secure in both generic and standard model around the turn of the century. Later, the landscape is further modularized and are extended to many fancier signature schemes, such as multi-signatures, ring signatures, and threshold signatures. However, there has always been a gap between standard model security guarantee and expectation of security in practice. In this work, we identify and close the gap via a discrete log-like problem, which we name multi-base discrete log. Let's start by recalling the Schnorr signature scheme and the underlying identification protocol. First, let's fix a group of prime order P with generator G. The secret key small x is sampled uniformly at random from ZP, and the public key big X is G raised to the small x. The signature scheme can be seen as the Fiat-Shamir transform applied to the underlying identification scheme. So, what is the Schnorr identification scheme? Well, Schnorr identification scheme is a 3-round protocol between the prover and the verifier. And the prover will take in input the public key X, which is also given to the verifier, but also, in addition, the prover has access to the secret key small x. In the first round, the prover will sample random R from ZP and compute G to the R, which is then sent to the verifier as commitment. Upon receiving the commitment R, the verifier will choose a random challenge in C from random from ZP and return it to the prover. The prover, upon receiving the challenge C, will compute a response Z as follows. And the response Z is computed exactly to make the verification equation hold. And the verification equation is G to the Z is equal to R times big X to the C. And upon receiving the response, the verifier will check indeed that the verification equation will hold. To turn this into a signature scheme, the Fiat-Shamir transform eliminates the interaction by hashing the random commitment R and message to be signed to derive the challenge C. In particular, in the signing algorithm, we'll first compute the random commitment. Then we'll derive the challenge C using the random oracle, a hash function model as random oracle, applied to the commitment R and message to be sent M. And the response is derived as before. Lastly, the signature is set to the random commitment and the response Z. Verifying a signature on a message M amounts to first deriving the challenge C using the hash function, and then checking that the verification equation indeed holds. The benefit of viewing the signature scheme in this modular form is that the UFCMA security of the signature scheme reduces to the IMP-PA security of the ID scheme. IMP-PA means impersonation under passive attack, and we'll recall it in a bit. UFCMA is the standard security goal for signatures and forgeability under chosen messages attack. This result was first shown by Abdallah N. Bellare and Namprampi. The lemma says that given an adversary attacking the UFCMA security of Schnorr signature, then an IMP-PA adversary can be constructed to break the IMP-PA security of the underlying identification scheme. And if Q is the number of random oracle queries of the UFCMA adversary, then there's a multiplicative loss of Q and additive loss of Q squared over P. This means that the core question here is the security of Schnorr ID scheme, and we can focus on it. Security against impersonation and a passive attack requires that a prover cannot impersonate if it only gives passive access to transcripts. In particular, it is modeled as a game, and in this game, the adversary will submit a commitment R, get back a challenge C, and to win the game, the adversary needs to provide with the correct response Z. And in addition, the adversary can at any point obtain valid transcripts via the oracle TR. When considering IMP-PA security of Schnorr ID scheme, we can largely actually ignore the presence of the TR oracle because of the honest verifier zero knowledge property of the protocol. The IMP-PA security of Schnorr ID scheme is typically proved based on assumed hardness of the L problem in the underlying group. The reduction uses rewinding, running the IMP-PA adversary twice in this, with the same commitment R to extract the discrete logarithm of the public key X. Since we essentially need 2 runs of the IMP-PA adversary to succeed, there is a square root loss in the advantage, as shown in the formula here. And we know that there's no known tight reduction from discrete log, and it's likely that none exist, as evidenced by Kiltz, Masny, and Pan. Now, of course, one can always assume that the IMP-PA's security of Schnorr directly in the group, but we ask, can we prove security from some DL type assumption that's independent of Schnorr identification? And before we answer this question, let us see why eliminating the square root gap in concrete security, it's important. Again, let G be a group of prime order P with generator G. Recall that the best known attack for discrete log on elliptic curves is basically for example using polar row, which achieves success probability of around t squared over p in time t. And in practice, is basically always assume that Schnorr identification scheme using group G will have the same security as discrete log. But with the current proofs, as shown before, this is not justified. In particular, there's the square roots. And so, for example, when P is a 256-bit prime, we compute, for 3 example values of running time, the corresponding upper bound on success advantage of any discrete log or IMP-PA adversary. And you can see that indeed the square root loss here does affect quantitative results. So this gap between theory and practice is unsatisfactory, and we'd like to do better via our new assumption. And the idea that to use different assumptions to justify security, it's really not new. And consider, for example, the Diffie-Hellman key exchange protocol. We do not know how to prove it from a discrete log, and so therefore we prove it from computational decisional Diffie-Hellman assumptions. And such scenario has essentially has happened in a lot, especially in parent-based cryptography. In that landscape, many bilinear group assumptions has been proposed to prove security of more advanced schemes such as IBEs and homomorphic signatures. Now, of course, these knobs cannot be turned without justification. The hardness of these problems must be justified in idealized models, such as generic GU models or algebraic GU model. And they need to be verified by cryptanalysis. And for these problems, the hardness is usually seen as becoming more well-founded as the problem ages. Whereas previous bodies of work turn these knobs to achieve feasibility of security, we ask, can we turn the knobs to tighten the reduction loss? And our answer to this is multi-base discrete log problem, or MBDL for short. Again, let G be a group of promoter P and with generator G. Let's first recall the game for DL, which simply samples a random target point Y and asks the adversary to produce the discrete log of the target point Y base G. The MBDL game adds the following on top of the standard DL game. First, additional to the target point Y, the adversary also get a list of random group elements x1 to xn. And they are sampled so that they are not identity elements. Second, the adversary is allowed to query a discrete log oracle, but only exactly once, specifying an index I and the group element W. The oracle shall return the discrete log of W base xi, where this I was chosen by in the input of the discrete log oracle. In effect, the adversary is allowed to take one discrete log, base any xi of his choosing. Lastly, again, to win the game, the adversary needs to find small y, which is the discrete log of target point big Y base G. Crucially, we know that the one query restriction on the discrete log oracle it's crucial. If not, if the adversary can obtain two queries of this oracle, then it can find the discrete log of Y base G trivially just by simply relating two calls of the discrete log oracle. Say first on the base G and then on the target point Y, but base x1. And the intuition on why such a problem could be hard is that essentially the discrete log oracle takes a discrete log, but with an unrelated point, which shouldn't really help to solve discrete log base G. And as suggested earlier, the only way we really know how to justify hardness of a problem is using idealized models. And we show here that MBDL is indeed hard in the generic group model. And in particular, it holds with the same quantitative bounds compared to discrete log. Okay, we now show how to prove IMP-PA security of Schnorr ID scheme from MBDL tightly. Recall that the IMP-PA game of Schnorr ID requires the adversary to produce a valid response Z for some randomly chosen challenge C and previously committed value R. Our theorem says that the IMP-PA advantage of any adversary A is highly bounded by the MBDL advantage of a related adversary B that can be constructed from A. And note that this relation is tight here and there's no square root loss. And the construction of B goes as follows. So first, let us note that if R, C, and Z is a successful transcript, then the response Z must be the discrete log of this group element, which is R times X to the C. So this means that the impersonator can take the discrete log of exactly this group element. So our goal will actually to be set this group element to our target point Y. And the reduction proceeds as follows. First, our adversary B will receive the base X and target point Y from the MBDL game. So here we're going to restrict to just n equals to 1 in MBDL. And the adversary will forward the base X as the public key for impersonator A. And upon receiving the commitment R, the adversary B will instead forward R inverse Y to the discrete log oracle. And so the discrete log oracle will compute the discrete log base X of this group element at R inverse times Y. And this is then forwarded all the way back to the impersonator. And the impersonator will respond with Z, and the adversary B will then use the Z as the guess for the small y. So let's see why the setting the value of R inverse Y as input into the discrete log oracle will work. Well, if C is a discrete log base x1 of R inverse Y, then it means that R times x to the C is Y. So they just simply by plugging this in, and this recall from earlier, if adversary is basically taking the discrete log of this value, then if it succeeds, then we have found the discrete log of big Y. So we have exploited using the discrete log base x to program y into this element to be equal to that element. So to sum up, we have constructed an adversary B that succeeds in finding discrete log of a target point y base g, taking exactly one discrete log base another unrelated base x, and therefore breaking MBDL. So we have showed that the IMP-PA security of Schnorr identification relates tightly to the MBDL in the underlying group. As mentioned previously, a positive result for Schnorr identification scheme directly translate to Schnorr signature because of the modular proof of security shown by AABN. Quantitatively, previous result says that when using a composition result by AABN, the IMP-PA and the so using the results of composition result and the IMP-PA to DL reduction, we get a bond of this form, and there's a square root around the discrete log advantage. But actually, if one were to do a direct proof using forking lemma, as done originally in Pointov and Stern, the Q here will actually go underneath the square root. Therefore, the eventual bound is a bit tighter. And our result says that actually no square root is necessary here. But we instead will rely on the hardness of MBDL instead of just discrete log. And we conjecture that for adversaries A and B with similar computational resources, MBDL and DL should be equally hard. And this has been verified if A and B are both generic algorithms, as we have demonstrated before. As comparison, we demonstrate that our result is indeed better if one were to instantiate parameters assuming only hardness of DL and MBDL. So here we're going to specify running time, running time and success advantage epsilon. And for for both DL and MBDL, we'll apply the GGM bound relating the group size P to the running time and the bound desired epsilon. And here we'll set T and epsilon to target a 128-bit security level, which means that we're setting T divided by epsilon to be 2 to the 128. And so here we can see that the group size required P2 is strictly smaller than the group size required P1. So P2 is the group size required from our results, and P1 is the one dictated by previous results. And this also shows the results in the speedup, which is also which is cubic in the bit size improvement. And similar results can be derived for Schnorr signatures, but in addition, we'll have to specify the allowed random oracle queries. We now discuss briefly how we justify the hardness of MBDL in the generic group model. Formally, in the generic group model, fix a set of strings G, and the game shall sample a random injective encoding function, mapping each element from ZP to some string in G. The game keeps track of a list of encodings GL, representing the set of elements that's known to the adversary. And the grouper operation is done via an oracle that takes two encodings of elements, provided that they are in the set GL, and the multiplication oracle will decode them, do the corresponding operation, and then encode them again to return this new encoding, as well as adding it to the list GL. The MBDL game stays the same, with the addition that in the generic group model, we add this oracle that does group operations. And we provide a theorem that says that if A is a generic group algorithm making Q OP queries, then the advantage of it breaking MBDL is at most this quantity, which is roughly Q squared over P. So here we give the rough proof outline for this. So first, we're going to fix some generic adversary making Q OP queries. And we're going to define an extended transcript to be of the form Z, which is the discrete log oracle response, Y, which is a target discrete log point, and the exponent x1 to xn. Note that this transcript fixes the behavior of the game if you also fix the randomness of the adversary, but it gives more information than what the adversary gets back. So the intuition is that the discrete log oracle query creates a one-dimensional constraint on these variables from ZP. And consider a real run of MBDL. First, we'll sample this small exponents x1 to xn, related to that they're now 1, and then we'll sample the targets y, and we'll compute the discrete log honestly, given some index I and group element w. And we'd like to argue that z and y here are independent. But as written here, they're obviously not independent, and they could have a correlation because w here could correspond to the element generated, by computing multiplication, for instance, of x's and y's. So let's move to a simulator run, in which we can argue this more easily. So instead of sampling all these at the beginning, we won't sample them at the beginning, and during the first and the only DLO query, we'll parse the representation of this element w into a product of xi's, so xi to the wi, and the product n times some power of g and some power of big Y. And it turns out that the response here can be sampled without needing to fix other values of x's and y. And in particular, there's kind of two cases. One is the trivial case, and one is the case when we can sample uniform at random. The trivial case means that kind of the response is determined already. And an easy case to think of is if this w is just xi to the wi and with nothing else, then we must return wi. So implemented into this intuition, actually there's more to check, and we'll have to fix all the other elements to kind of sample whether we're in the generic case or not. And if it is, we'll set z to wi, and then we'll sample this xi uniform at random. And if not, then we sample z uniformly at random, subjected to it not being this value wi, and then solve for xi. And we provide a lemma that proves that these two ways of sampling the transcript provides identically distributed distributions on these transcripts. And with this lemma, the proof will proceed as other GGM proofs, modifying E to be lazily sampled via game hops while incurring a loss or overall loss of the form Q squared over P. One thing to note is that KMP has previously claimed a tight reduction of Schnorr identification from discrete log. Their notion of tightness is ratio based. In particular, they define a reduction to be tight if it preserves the ratio between the running time and success advantage. Our view is that this definition of tightness does not actually translate into tight security guarantees in practice. Indeed, like both attacks and bounds for DL type problems indicate a quadratic trade-off between success advantage and running time. So our view is that tight reduction for group-based schemes should preserve both running time advantage independently. And we show that this does translate to tight security guarantees in practice. And finally, we believe that MBDL as a DL-like assumption can be applied in other settings. In particular, MBDL can eliminate the need for rewinding in forking lemma-based proofs. For example, Drivers et al. Has shown that multi-signatures, fork lemma usage in multi-signature can be error-prone, leading to insecure schemes. And in the follow-up work, we show that MBDL can be used to prove security of other schemes, such as the Bellare-Nevin multi-signature schemes, music, 1 out of n signatures, threshold signatures, and as well as new 2-round multi-signatures based on an extended version of MBDL. And that is the end of my talk. Thank you for tuning in.